Hello, I'm Ryan Cosner, and I'll be presenting the work entitled Measurement Robust Control Barrier Functions, Certainty and Safety with Uncertainty in State. This is joint work between myself and my collaborators, Andrew Singletary, Andrew Taylor, Tamas Molnar, Katherine Bouman, and Ames. This work is motivated by safety-critical systems, which are systems such as automobiles, airplanes, and medical robots, where, due to their interaction with humans and their costs, safety failures for these systems are unacceptable. We're also motivated by the increasing complexity of available sensing methods, such as onboard cameras. Utilizing these sensors introduces new errors into the system, which may cause unsafe behavior. For example, here we visualize how errors in these systems may affect the system behavior. We consider the Segway robot safe if it remains left of the red line. The solid image represents the true position of the Segway through time, and the translucent blue image represents how the position is estimated by the onboard camera. It is possible that due to measurement error, the measurement of the system may be safe while the true system is not. Thus, we seek to find a method by which to guarantee the safety of the true system even in the presence of these measurement errors. To do this, we look to leverage measurement robust control barrier functions and implicit safe sets to guarantee the safety of the Segway robot with vision in the loop state estimation. For this work, we consider nonlinear control affine systems. In addition, we define safety as the invariance of some safe set C. We define this set as the zero superlevel set of some function h. For example, in the scenario of the Segway, we can define the safe set as everything left of the red line through the use of a linear function h. Here, we introduce control barrier functions. We call h a control barrier function, or CBF, if for all x in the safe set C, there exists a u such that the time derivative of h satisfies this inequality, where alpha is an extended class K function. An important result is that if this inequality is satisfied, then the safe set C is invariant. Natural properties of the system, however, may make it difficult to find such controllers. For example, consider the case of the double integrator, with position on the x-axis and velocity on the y-axis. Assume that safety is defined by the position of the system as seen in the green safe set C. If the controller u can satisfy the inequality, then the system is safe. But for points such as this one, that is not possible. This is because this point has a positive velocity on the boundary of the safe set, so it must leave the green region and become unsafe. Sets such as this one cannot be rendered safe by any bounded controller. Alternatively, sets that can be rendered safe by some controller are called control invariant sets. One example of a control invariant set for this system is this one. In this case, the system's velocity must slow to a stop as it approaches the original position boundary, and thus it is not required to instantaneously stop as it was before. The control invariance of the safe set is particularly crucial for a Segway robot due to the non-minimum phase nature of its dynamics. Here we discuss a method for finding control invariant sets. We'll visualize this method on the right using a double integrator, which we would like to keep inside of a region of bounded position. We first start with a small set CB, for which we have a controller KB that renders it safe. We will call this a backup safe set and a backup controller. For example, this could be a Lyapunov sublevel set for an LQR or CLF controller. We can now expand this set using the backup controller. We do this by considering the flow of the system from point X under the influence of the backup controller KB. We denote this flow as phi. We now require that two conditions hold. One, that the flow of the system remains inside of the safe set C during a time interval 0 to t, and two, that the flow reaches the backup set CB by time t. This ensures that the system stays safe with respect to the original position-based safety criteria, and that there always exists a controller that renders the system safe for all time. Together, these conditions define our implicit safe set CI. Notably, this implicit set can be described as the intersection of zero superlevel sets. In order to render the system safe with respect to CI, we can enforce the CBF constraint on the equations which define the implicit safe set. These appear as linear constraints in a quadratic program controller, which we will call the backup set quadratic program, or BSQP. For brevity, we denote the composition of the function h with the flow phi as the function h bar. This controller filters a desired controller KD and finds a control action which will keep the system within the implicit safe set. We note that one of the constraints was converted from infinite to finite by taking discrete samples of the prediction time. The parameter mu was used to strengthen the constraints to ensure that satisfying the finite conditions ensures that the infinite conditions are also satisfied. This controller can be easily implemented on real-time embedded systems since it is a quadratic program. In this video, we show how the BSQP controller helps ensure the safety of the system in practice. On top is the Segway without the BSQP controller, and on the bottom is with it. This works well in a lab setting, and our goal is to extend it to other scenarios and incorporate other sensing modalities. For example, we would like to bring the Segway platform outside and introduce cameras to use as a state estimator. Here, we show our model for how this can introduce error into the system. First, we map the true position of the Segway x to a sensor measurement y using some function p. In this case, the sensor measurement is the camera image feed. Next, we use a state estimator q hat, which maps from the measurement to an estimate of the state x hat. This estimate may not be correct, and we denote this error as the function e of x. We further assume that this error is bounded. Here, we show how we can incorporate error into the CBF condition. First, we take the infimum over the possible error. We additionally take advantage of the control affine structure of the system to write it as the following, using the Lie derivative terms LFH and LGH. Next, we convexify the infimum and write the condition in terms of the measured state x hat. The added terms are epsilon, which is the bound on the measurement error, and the script L terms, which are the Lipschitz constants of the subscripted functions. Functions H, for which this condition can be satisfied, are called the measurement robust control barrier functions, or MR-CBFs. We can now apply this robustification method to the constraints of the BSQP shown here. To do this, we strengthen the required condition to that of an MR-CBF. We do this by adding the robustifying Lipschitz and epsilon error terms. We call the implicit safe set Ci a measurement robust implicit safe set if, for all x in Ci, there exists a U which satisfies these constraints. We now present our main theoretical result. Given our supposed measurement model, and a measurement robust implicit safe set Ci, if a controller U satisfies the robustified constraints, shown here, then the system is safe. We additionally note that these constraints can be easily implemented in an optimization problem as a safety filter, as we did with the BSQP. We call that controller the Measurement Robust Backup Set Optimization Program, or MR-BSOP. We also note that this can be efficiently written as a second-order cone program, and is solved efficiently enough for real-time control applications. Now we will discuss our experiment. This is the experimental Segway platform that we used. It is a customized 9-baud E+ Segway. For forward position estimation, we used an Intel RealSense T265, which was running visual inertial odometry and SLAM. For the estimation of all other states, we used wheel incremental encoders and a vector nav VN100 IMU. For onboard computation, we used a Jetson TX2, which was running ROS in a Linux environment, and also the Erica 3 RTOS. We used the ECOS solver to implement the MR-BSOP as a second-order cone program which ran at 250 Hz. For our experimental setup, we took the Segway outside and stacked some boxes in front of it. We defined the safe set to be any x position less than 2 meters, and we assumed that the starting point was at 0 meters. For a backup controller, we used an LQR controller on the linearized dynamics. And for the backup set, we used an estimate of the LQR region of attraction to an upright position inside of the safe set. To implement the MR-BSOP, we used 4 discretization points and a time horizon of 1 second. The Lipschitz constants were estimated analytically and by state space sampling. We first implemented our experiment in simulation, where we artificially injected an error of negative 0.4 meters into our system. Here, the green rectangle represents the safe set, the solid line represents the true state, and the dashed line represents the measured state. In the center, we can see that the BSQP failed to keep the system safe. On the right, we can see the results of the MR-BSOP controller. We also added a blue patch to indicate the set of states which the controller will keep safe. From this plot, we can see that the MR-BSOP succeeded in keeping the Segway safe where the BSQP failed. Now, we'll show a video of the hardware experiments. First, we'll be using the BSQP, and next we'll be using the MR-BSOP. Shown here are the results of the experiment. As before, the green rectangle represents the safe set, the solid line represents the true state, the dashed line represents the measured state, and the blue patch represents the states kept safe given the measurement error bound. We also add a blue line below each plot to show the error introduced by the Intel RealSense camera. As with the simulation results, we see that the MR-BSOP succeeds in ensuring safety where the BSQP failed. In conclusion, we proposed a method to synthesize robust controllers with formal safety guarantees for systems with uncertain measurements. Furthermore, we demonstrated the robust safety guaranteed by this method on a Segway platform. For more details on this work, please see the associated paper which can be found at the link provided. Finally, we'd like to thank AeroVironment, British Petroleum, Dow Chemical, the National Science Foundation, and Caltech for their support of this work. Thank you very much for listening.